Namaskar my dear friends. So we have seen the design and detail of LT8602. This is a switching regulator which is having quad outputs, that is 4 outputs are there. So in this session what we will do is we will try to understand how we can design this particular IC for different outputs for our automotive systems and some other applications as well. Okay, so we'll directly get into the design implementation and design examples, and we'll also try to find out how we can design the equations and how we can calculate different values for the output voltages. Okay, so the thing is this can be utilized in your automotive cluster design power supply solutions, as well as it can be utilized in your automotive infotainment or industrial control power supply systems. So basically all these systems actually use processors and SoCs, and to power supply these processors and SoCs, this particular IC can be utilized. Okay, so we have already seen this is having basically two particular pin configuration. One is 40 pin QFN package, and one more is 48 pin LQFP package. Okay, and both of them are having exposed pad. Okay, so exposed pad is there which will help you to have heat dissipation properly. So now we'll directly get into the application circuits. So as you can see in the data sheet itself, we have one application circuit which is basically details of front page application. Okay, so details of front page application. In this you can see the design and detail that is given as the input voltage is 6 to 42 volt. Okay, so let us say we are going to give a 12 volt power system supply. Okay, and we have output of 5 volt, 3.3 volt, 1.8 volt and 1.2 volt. Okay, so same thing was actually utilized in one of our system for one of the PCB that we had designed for our instrument cluster, automotive clusters. Okay, so as you can see the values of like inductor and R1 and R2 for feedback pins. Okay, so these are the three things that we have to calculate for the like output regulation, like out 1, out 2, out 3 and out 4. Okay, so this is how we are going to design our circuit. Before that what we have to do is we have our input like pins, that is V input and PV in 1 and PV in 2. So both of them will be supplied with a bypass capacitors and some filter capacitors. Similar to that we have track and track pin. Okay, tracking and smoothing pin, soft start pin kind of thing. So tracking and soft start pin is there, which will be grounded with 2.2 nanofarad. This is 2.2 NF. Okay, similar to that we have run pins and we have power good indicators for all the 4 channels, that is PG1, PG2, PG3, PG4. So in our design we will give you complete understanding of how we have designed the power good indicators. Similar to that we have sync pin. So sync pin is actually used to have a synchronization with a clock of outside world. Okay, so suppose you have a clock signal from outside SoCs, or maybe you have some FPGAs, so that clock can be utilized. Otherwise there is a RT pin which will set the like a switching frequency that is there for your IC. So for 60.4 kilo ohm it is going to set your switching frequency to 1 megahertz. Okay, coming back to internal VCC, that is basically utilized for your internal functionalities. So this is going to be like a pull down or like bypassed with 4.7 microfarad. So this is going to give you output of around 3.3 volt, or basically equal to bias voltage. So bias voltage is here, that will be utilized. Okay, now proceeding to the BST1, which will be having 0.1 microfarad to switch 1, and BST2 which will be 0.1 microfarad to switch 2, and switch 1, switch 2, switch 3 and switch 4. All these pins are going to have their proper inductors, and these feedback pins are going to have a resistor divider design so that you can regulate your output voltage, and the output capacitor must be taken into account properly so that it can drive the load without any ripple or without any noise. Okay, so with this information what we'll do is we'll directly get into the designed circuit that we have done. Okay, So let us say this is the design that we had done. Okay. In the last session also we had explained you very clearly or very easily that what is my input voltage. Let us say this is my 12-volt input, and I have given this pin to in V in and PV in 1, PV in 2 both. Okay, so PV in 1 pin are 2 pins and PV in 2 pins are also 2 pin, and V in pin is 1 pin. Okay. So what you have to do is 22 microfarad plus 1 microfarad. So these two like capacitor has to be very close to V in pin. Similar to that, one more pair of 22 and zero point 0.1 microfarad will be near to PV in 1. Okay, power voltage input 1, and similar to that, one more pair of 22 microfarad and 0.1 microfarad will be very close to the PV in pin 2. Okay, so this is how capacitors will be like placed. Got it? Similar to that, the voltage output was there for like high voltage outputs, that is switch 1 and switch 2 are actually high voltage converters, and switch 3 and switch 4 are low voltage converters. Okay, so low voltage converter means, let's say you have to have a voltage output requirement of 1.8 volt or 1.2 volt, or even lesser than like 1.2, that is, let's say 1 volt or 0.85 volt or 0.75 volt. So basically these voltages are used in your SoCs or like processors or FPGAs. Okay, so these are the reasons we need a very low voltage output with very high current. Okay, so one of the output of high voltage in the high voltage converters is used as input to the low voltage converters. So that's the reason 3.3 volt has been used at PV in 3 and PV in 4, and similar to that 10 microfarad plus 0.1 microfarad will be close to PV in 3, and one more 10 microfarad plus 0.1 microfarad will be close to PV in 4. Okay, so this is how we are going to design. Coming back to PZ pin, so that is power good indicator. So power good indicators has been pulled up with 3.3 V. Okay, and it is going to go to our microcontroller or my FPGA, where it will be giving you the indication of whether the output, I mean voltage output, are correct values or not. Okay, or within the range or not. Okay, so as you already know that FB1 and FB2 are set to 1 volt, and FB3 and FB4 were up at 0.8 volt. Okay. Now I will open one Excel sheet and show you how we can calculate this particular like feedback resistors values. That is, it is here 453 Kelvin and 453 kilo ohm and 113 kilo ohm for 5 volt output. Okay, and we have the inductor value of 6.8 microhenry. So these particular three values will be utilized for 5 volt output with 1.5 ampere rating. So I have 1.5 ampere rating for 5 volt output. So let me calculate and show it to you so that you can calculate for other as well clearly. Okay, so this is the calculation sheet that I have taken. So what we have done is, we have the input voltage which is 12 volt. We have the switching frequency that we have set it to 1 megahertz. PV in pin we have set to 12 volt only. Okay, so PV in 1 and V in input both are same. Okay, let us say my user input is V out 1, which is going to be 5 volt. Okay, so we know FB1 is 1 volt. Okay, and if you utilize this particular formula, you will be able to calculate your value of R1 and R2. So R1 is equal to R2 into V out X by V reference, feedback voltage reference, minus 1. So let us say R2 value is assumed to be 113 kilo ohm, then R2 will be 113 kilo ohm, then R1 will be calculated as 452 kilo ohms. Okay, so that's the reason there it was used for 153 kilo ohm approximately. Okay, if you want, you can utilize 110 kilo ohm, let us say, then it will give you 440 kilo ohm. Similar to that, let's say 105 kilo ohm if you use, then it will be 420 kilo ohm. So whatever the like values that you utilize, accordingly you can calculate your R1 values. So this sheet I will like give you based on your requirement. If you need, I can share this particular calculation to you. Similar to that, coming back to the inductance calculation, so what happens is K1, K2, K3 values were there, which were actually 1.6, 1 and 1.3 and 1.3 for K1, K2, K3, K4 values from the data sheet. Coming back to L1 value calculation, so L1 value calculation can be calculated with this particular formula, which is Lx is equal to Kx into V out x by PV in x into PV in x minus V out x by Fs. Okay, so Fs is 1 megahertz that is taken. So if you see, L1 value is coming to be 4.67 microhenry. So your aim must be to like utilize a value greater than this or equal to this. Okay, so what you have to do is, let's say we have considered to be around 6.8 microhenry. Okay, or 4.7 microhenry will also do. Similar to that, you have to understand what is the maximum output current that you are looking for. Okay, so you put that value, which is your 1.5 ampere, and similar to that, the ripple current that you have to calculate using this particular formula, which is going to be delta ILX is equal to V out x by LX into Fs multiplied by 1 minus V out x by PV in maximum. So PV in maximum I am considering 12 volt only. Okay, and if you want to utilize more, then you can use more, and this is how ripple current will increase. Okay, so let us say that this particular value I am going to take up, I1 out I1 out maximum is equal to 1.5 ampere, and it is going to give you IL max that is going to come up as 1.81 ampere. So what is the advantage of this particular value? So the advantage of this particular value is to check, let us say we have the inductance that we have selected, which is going to be 6.8 microhenry. So what is the current rating that will be there for this inductor is more than this. Okay, so you try to have at least 2 times or 3 times of this. Okay, so this will be better. So that's the reason we are selecting around 4 ampere rating or like 6 ampere rating of this particular inductance. So this is the process that we have calculated our V output 1 of 5 volt plus 1.5 ampere rating. Okay. Similar to that, for PV in 2, I have the input 12 volt itself and V output is 3.3, and coming back to FB pin is 1. So let us say we are going to have R2 pin as 100, R2 as 137 kilo ohm, then R1 will be calculated to be 315 kilo ohm, that is taken to be 316 kilo ohm. Okay. And corresponding to that, L2 will be calculated to 2.39 microhenry. So if you wish to, you can like utilize close to this particular values, or you can go ahead with 3.3 3.3 microhenry. Okay, coming back to PV in 3. So PV in 3, I am going to take this voltage output as voltage input for PV input 3, and in that case you are going to have PV FB3 is 0.8, right? In the data sheet it was given for FB3 as 0.8, and with this particular same formula R1 R2 will be calculated. So let us say I want to use R2 as 120 kilo ohm, then R1 will be calculated to 150 kilo ohm. Okay, so this is how you can change your values based on your calculation. If you want, you can utilize some other values as well, no problem. Let us say in the data sheet it was given to be how much? 200 kilo ohm, so it is going to calculate as 249 kilo ohm. Okay, so what will happen? Let us say I am going to take 200 kilo ohm R2, then 249 kilo ohm will be coming to be the value of R1. Okay, so I will not change it. I am liking this value of 120 kilo ohm, so that's the reason I am going to utilize 150 kilo ohm. Okay, similar to that, coming back to PV in 4. So PV in 4, the voltage input will be same PV in 3. So what will happen is, let me just calculate this. This is the value of PV in 3, PV in 4. So PV in 4 is 3.3, and V out 4 is 1.2 volt, that we have set it output voltage of 1.2 volt. So what is the feedback voltage that was there at channel number 4? That was 0.8 volt. And if we consider R2 value as 150 kilo ohm, then R1 will be calculated to be 75 kilo ohm. Okay. Now let us say same way L3 and L4 has been calculated, which is close to like 1 microhenry. So if you want, you can utilize 1 microhenry, or you can go ahead little bit higher values, which will be 2 microhenry, and this can be taken as 1 microhenry. Okay, and their I out maximum is taken. So based on that, you have to make sure that your saturation current must be at least twice of this values that you have calculated. Okay, good. So all these calculations are done. I hope you have a good understanding of this particular like calculation sheet. And if you do need to like have a little different values, let us say my output voltage is required to be 7.5 volt. So for 7.5 volt, what you can do is, if R2 value you select to be 105 kilo ohm, then R1 will be considered to be 682 kilo ohm. And if you take R2 value as 150 kilo ohm, then R1 will be calculated as 975 kilo ohm. So we can keep it, let's say 100 kilo ohm itself, that is going to be 650 kilo ohms. Okay, so based on this output value settings, you can calculate your R1 R2 for your feedback resistor network, and this is how you are going to design your circuit. Alright guys, hope you have a good understanding of the like calculation of all these inductors and feedback resistor networks for each of the output and current setting for the output required. Okay, so do let us know, like if you need any other like explanation regarding this particular IC design, and if you do have any other requirements of your output settings, or if you have a query of utilizing for your like any other applications, which kind of IC to be selected, or whether this particular IC is suitable for your particular design, that also can be like answered to you very easily. Let me give you two more examples that were there in the datasheet directly. So I'll just like quickly go through them, and it will be easy for you to understand how they have designed it. Okay. So there is a design which was given as like automotive input steps down to 5 volt, 3.3 volt, 1.8 volt, and 1.2 volt. Okay, so the current rating you can see like 1.5 ampere, 0.8 ampere, and 1.7 ampere, and 1.8 ampere. You can see there is a like trick here, that the output 2 has been utilized as a input to the like power input 3 and power input 4. Okay, like PV in 3 and PV in 4. Where is that? You can see yeah, we have here PV in 3 and PV in 4, so that is directly taken as power output, voltage output of channel 2. Okay, so that's the reason where they have considered that this output was actually 2.5, but the remaining, because of 1.7 ampere at output 3 and output 4 at 1.8 ampere, you are going to lose some of the current at channel 2 output. Okay, and that remaining will be 2.5 minus this whole I out 3 and I out 4. Okay, and that's how you are going to land up only up to 0.8 amperes. Okay, so that's the reason you can utilize the same concept here, and you can change your settings. So let us say I out 2 max, instead of 1.5 amps you can put it 2.5 ampere, and this is how you are going to get your IL2 maximum at 3 amperes. Okay, and similar to that, here I out 3 and I out 4 you can change it based on your requirement. 1.7 ampere is there, and similar to that it will be 1. Let me just see once. It is 1.8 ampere, so 1.8 ampere you have to put. Okay, so this is how you are going to have your IL maximum that is required at the output. Okay, good. Based on this and similar to that, the output setting, voltage setting, same resistors can be utilized because the voltage is not changing. So 5 volt, 453 kilo ohm and 113 kilo ohm is fine. Then 316 kilo ohm and 137 kilo ohm is fine. Then if you want, you can change these two values for use with our calculation. That was how much? Let me just show it. This was 120 kilo ohm and 150 kilo ohm, and 150 kilo ohm and 75 kilo ohm. Okay, so this can be 120 kilo ohm and 150 kilo ohm, and then this will be 120 kilo ohm and 75. Sorry, R2 was actually 150 kilo ohm, 150k, so this will be 120k. Let me just see once. R2 is 120 kilo ohm, then R1 is going to be 150 kilo ohm. Okay, so R2 is 120 kilo ohm. I am going to do that. R2 is 120k, then R1 is 150k for channel 3. Now for channel 4, my R2 is 150k, then R1 is going to be 75k. Okay, so this is how you are going to get your output voltage at 1.2 volt and 1.8 volt. So this is another application that was there for like automotive application. And make sure your output capacitors are having a good amount of values, like 22 microfarad. If it is not sufficient, you make it change to 75 microfarad. Also, my suggestion would be to have a parallel combination of at least two capacitors. Okay, so to 22 microfarad, 22 microfarad, and plus definitely you keep one 0.1 microfarad capacitor in each of the output. Okay, so this will serve a very good smoothing capacitors or maybe a filter capacitor. So each one of them you put one 0.1 microfarad capacitors, and sorry, and here also 0.1 microfarad capacitor. I'll suggest you at output 3 you can utilize one more parallel 22 microfarad capacitor, and here you can leave it 47 microfarad capacitor. Similar to that, make changes at the input. So input, what you have to do is PV in 1 you have to make change with keep 122 microfarad capacitor, okay, and plus 0.1 microfarad capacitor. Okay, similar to that, same changes you do with PV in 2 as well. Okay, and coming back to PV in 3, so PV in 3 and PV in 4 you keep a 0.1 microfarad very close to each other. Okay, very close to the PV in pins. Okay, 0.1 microfarad. Coming back to V in pin, so V in pin separately you keep 10 microfarad capacitor and plus 0.1 microfarad capacitor. So with these changes you will be able to utilize the exact same circuit for your application. Okay, if you do not need any under voltage lockout features, then you can delete all these and directly sort the V input to your enable pin. Okay, so there is no need to have under voltage lockout method, then you can directly sort it and keep it to enable. Coming back to PG1, PG2, PG3, PG4, so all these 4 pins you can have a pull-up resistor with 3V3, okay, of 20k, and each one of them, let's say PG1, then similar to that PG2, like that you can connect, and all these PG1, PG2 you can take it to your microcontroller or like FPGA IOs pins. Okay. Here you can see the switching frequency was set to 1.25 megahertz. So for that you have a requirement of RT resistor that is going to be 47.5 kilo ohm. So based on this particular frequency settings, the calculation of inductor is there, which is 4.7 microfarad, 2.2 microfarad, and 1.5 microfarad and 1.2 microfarad. If you want to decrease the switching frequency, then the inductor value will change accordingly. So you can utilize this particular sheet for your own switching frequency requirement, and accordingly the L values will change, the inductor values will change. Okay, so please make these changes and do your design for your suitable automotive input step down regulators for this particular voltage outputs. Okay, and if you have still a requirement of complete design support or something like that, you can always reach out to us and we shall be able to answer you out with your complete design with your part numbers of each of the capacitors and inductors. Okay, so generally capacitors and inductors part numbers only will be required for you to design this particular schematic. Resistors are very easy to get. All the resistors can be taken 0603 package. Okay, so all the resistors 0603 package of 0.1 watt or 1/10 watt is more than enough to utilize. Let me explain you one more example that was given in the data sheet, which is actually 10 volt to 42 volt input and steps down to same 5 volt, 2.5 volt, 1.8 volt and 8 volt. Okay, so there is a change here, 8 volt is there. So what is done here is channel 1 is used to be 8 volt, and accordingly you can calculate your values of R1 and R2 for your 8 volt output. Okay, so here it is made 143 kilo ohm, so that you are going to get 1000 kilo ohm, that is 1 mega ohm for R1. And accordingly value of L will be calculated based on the switching frequency that is set here. So switching frequency is set to be 2.2 megahertz. So I'll suggest you don't go ahead with 2.2 megahertz, go ahead with like around 1 megahertz always. So this is very good choice, okay, or 1.2 megahertz or 1.2 megahertz max. Okay, so that values you can always select based on the switching frequency resistor setting that is given in the last video. Okay, coming back to other changes, what will you do? The voltage setting is done already, FB1 FB2. Then similar to that you can set the voltage settings for output 2, output 3 and output 4. The changes that will come here is you can see the PV in pin 3 and in 4, that is actually taken from output 2, which is going to be 5 volt. Okay, so 5 volt will be the input for the PV in 3 and PV in 4. You have to make sure that PV in 3 and PV in 4 do not get input more than 5.5 volt, that was given in the data sheet. Okay, and just now I mentioned all the capacitors that you can change and accompany with 0.1 microfarad capacitor in each of the lines. Okay, just like previous explanation I did here. Okay, and similar to that, at the input pin of PV in 1, PV in 2, you can increase the capacitor value with 0.1 microfarad filter capacitor, so that it will be easy for your design. And if you want, you can remove this particular under voltage lockout, so that you don't have to struggle with under voltage lockout conditions and all, and you can use your enable pin directly to the V. Okay, good. So if you do have any questions regarding this, like how we can design our power supply system, or this is a very good IC, quad input quad output step down regulator. So this is the reason this particular IC I am stressing a lot, and this particular IC has been used in many of the application in our automotive application, as well as many industrial cluster design that were there. Okay, so alright guys, if you do have any questions, please reach out to us, and do like and subscribe our channel, and we shall be able to come up with any queries that is there with you to our query box. Thank you.